Maybe he or she is too shy.
So we continue in English.
Ну, надо всех попросить, чтобы самое список отсутствующих.
Okay.
Я так делаю в группе.
Незачетно. Okay, I will talk in English. So although most of the attendants of this seminar are topologists, let me start with general mathematical problem, namely Netflix problem. So first, informal industrial problem, given some matrix representing the rating of some movies by customers. There is an ICE movie, NG customer. Then at this cell we have the
Rating.
the rating of ICE customer for J movie.
Maybe you can say this in Russian. Оценка этого фильма жителям клиентам.
Да.
Наоборот.
Да. Of course, not the entire matrix is known, and the problem is to complete matrix so as to make good predictions. And a mathematical formalization is as follows: we are trying to minimize the rank of the obtained matrix. So some entries are known, some are unknown, and we take unknown entries so that the rank of the obtained matrix is minimized. I didn't find any heuristic for this idea. I think it's just people do this and they obtain good results, and they have no any theoretical justification of this minimization of rank, even heuristic. Well, actually, not only me, but some people from computer science also tried to find a reference for heuristic, but didn't find it. Can I move this? So, of course, in this very problem, the entries are real numbers, not residues modulo 2. But for simplicity and for application of topology, we only consider matrices with 0 or 1 entries and unknown elements. So we start with some particular case when all entries except the entries on the diagonal are known. And minimization of rank occurs at the price of changing diagonal elements with application to topology. And then we go to a generalization. We consider not matrices with given elements, but matrices with some relations on elements. And we try to minimize rank under these linear relations. In principle, this can be called quantum analog of Netflix problem, but in this case, these relations do not have any probabilistic nature. So this interpretation, this word is not very well, not very proper. So of course, I will study this for topological applications. First, embeddings of graphs in surfaces, including so-called embeddings modulo 2. And of k-dimensional hypergraphs to k-dimensional surfaces.
So is k-dimensional hypergraph the same as a k-dimensional polyhedron? There is something. For the purposes of such an introduction, yes. So of course, complexes and hypergraphs are different notions, but at this level they are the same. And so this talk is based on is mostly based on joint results with Eugene Kogan and will only briefly mention joint results with Slava gender. Maybe at this very point, I will uncover the secret why there is a relation between Netflix problem and topology. And this relation occurs because of the existence of an intersection form onto k-dimensional manifold. So intersection form is a matrix, right? And in some situations, studying this matrix amounts to Netflix problem and its generalization. So let me start with some very simple example. This is weak realizability of graphs in surfaces, and we only consider very simple graphs, with those having only one vertex. Although these results have straightforward generalization to arbitrary graphs, but this case is most simple and most interesting. So an hieroglyph on n letters is an unoriented cyclic letter, cyclic sequence of letters of length to n, such that each letter appears twice. So let me draw a word corresponding to this picture. This I call A, B, C, and D the wedges of this graph, and I go around this vertex, and so write the cyclic word A, B, B, C, D.
Да, но вас не видят, наверное.
I have to switch it on.
Ну, продвинутые это видят. Да, можно сделать.
Yeah, this is an example of a letter A, C, D, D, C, D, B corresponding to this picture. So although formally an hieroglyph is a word, but of course there is a topological picture, a picture corresponding to this word. We go back to the text. Okay, I think I should better go to the picture again. So this should better be explained on the picture. Having this hieroglyph and having this picture, we can make a two-dimensional surface out of it. Just take a two-dimensional disk and attach ribbons to this disk along the edge of the graph, that is along the loops, along these loops. And in principle, for each ribbon, we can take either such untwisted ribbon or a twisted ribbon like this. So how is this called?
Twisted one time or three times? Is there a difference?
No matter. So the obtained surface is disk with ribbons corresponding to the hieroglyph. And actually, here are some pictures of disks with ribbons. So of course, we study disks with the ribbons up to homomorphism. So it only matters whether there are even number or odd number of twistings. And if I show it this way, can people see it? So this is a very particular hieroglyph, which is in some sense standard. It's a disk with 3 Möbius bands, and analogously one defines the disk with n Möbius bands. And it is of course homomorphic to the standard non-orientable surface,
that is to connected sum of n RPNs, of n RP2s, with the whole deleted. So realizability of a graph on this disk with Möbius bands is the same as realizability of a graph on a standard non-orientable surface.
And the realizability is same as embeddability.
Yeah, realizability is the same as embeddability, but let me now introduce a different notion. What is a weak realizability? An hieroglyph H is called weakly realizable on the Möbius band, or on the Möbius band or on the disk with some number of Möbius bands, if some disk with ribbons corresponding to this hieroglyph can be cut out of the Möbius band, or mathematically is embeddable into the Möbius band. So that is, weak realizability is not realizability of some particular graph, and even not realizability of some particular graph with rotations. It's realizability of one surface among several number of surfaces. If there are k letters, okay, I can tell this without writing. If there are k letters in the hieroglyph, then we can construct 2 to the k disks with ribbons corresponding to this hieroglyph. And of course, some of them can be homomorphic, so there is a smaller number than 2 to the k of homomorphic classes. And weak realizability is realizability of at least one of these 2 to the k surfaces.
It comes from the choice of orientation on each band.
Not orientation, but twisting or not twisting. Yeah. So for this reason, of course, given this choice, we have a surface, and of course, it is very easy to check whether one surface embeds into the other surface, mathematically or algorithmically. So in principle, there is an algorithm which recognizes weak realizability of an hieroglyph in the Möbius band or for given k in the disk with k Möbius bands. But this naive algorithm is exponential. It has 2 to the n steps, where n is the number of letters in the hieroglyph or of ribbons in this construction. And the idea is to find a polynomial or even linear algorithm. So let me state the results. Trivial. So this is a theorem. One is part A is by Arkadiy. Then there is an algorithm with the complexity n square, deciding whether an hieroglyph on n ribbons is weakly realizable on the Möbius band. So the point is not the existence of an algorithm, but complexity, polynomial complexity instead of exponential complexity. And a generalization to disk with k Möbius bands, it's due to Eugene Kogan. For any fixed k, there is an algorithm with the complexity n to k plus 3, deciding whether an hieroglyph with n ribbons is weakly realizable on the disk with k Möbius bands. So let me explain why this result holds and what is, let me explain simple and interesting topology behind this result. And in fact, these results are based on realizability criterion in terms of the intersection form of a surface. Let me introduce this well-known criterion. So for this, I will introduce the overlapping matrix of the hieroglyph, very natural notion. 2 letters N, B, and hieroglyph H overlap in this hieroglyph if they interlace in the cyclic sequence of the hieroglyph. So perhaps I will switch off
the screen and give an example.
So it is about linking of two zero-dimensional spheres.
Yeah.
In the circle.
Yeah. So in this sequence, in this cyclic sequence, no two letters overlap, no two letters interlace. But here is an example of a cyclic sequence in which, well, letters A and B interlace. Well, and the overlap matrix is defined as follows. Put zeros on the main diagonal and put 1 in the cell ij if the letters I and j interlace or overlap, and put 0 otherwise. So a very natural construction. And then for a matrix M of size n times n with the two elements denoted by R of M, the minimal rank of all the matrices obtained by changing some entries on the main diagonal of this matrix. So this is now a definition from the Netflix problem, from a particular case of the Netflix problem.
What is some entries? Any number of entries?
Any number of entries, yeah, right. So in order to calculate R of M, we have to check, we have to consider 2 to the n matrices. At least if we are doing this naively. Well, and here is a well-known result. A hieroglyph is weakly realizable on the Möbius band if and only if R of its overlap matrix is at most 1. That is, if one can change diagonal elements in its overlap matrix to obtain a matrix of rank at most 1. And a natural generalization, a hieroglyph is weakly realizable on the disk with k Möbius bands if and only if we can change diagonal elements of its overlap matrix so as to obtain a matrix of rank at most k. And even though this seems to be unusual, this is actually a well-known result. So I found a reference to Moher paper of '89, but of course it's sort of folklore result known much earlier. We just okay, let's see. If we take the overlap matrix, then having untwisted or twisted ribbon corresponds to the square of this particular element of in homology being 0 or 1. And this means that twisting or untwisting defines diagonal elements of this matrix. And that's why by choosing diagonal elements on this by changing diagonal elements of this overlap matrix, we check the embeddability of the corresponding disk with ribbons on given surface.
Arkadiy, вопрос, извините, по-русски. Значит, матрица вот этих самых булевых матрица рассматривается?
Какой булевый?
0 и единица.
А только такие рассматривают.
Только такие.
Да, ну, в этом докладе.
Да.
В жизни как раз настоящее в этом докладе.
Все только в голове.
So a question. Both sides of this theorem involve considering 2 to the k cases. Yes. So is there a theorem without any cases?
Well, this is a well-known topological theorem on which the proof of that theorem is based, right? And so the results of BKF and Kogan, they follow from this known result and their own result, which allow to calculate well, R of M in polynomial time. And those results are, well, just elementary algebra on one side, but on the other side, on the other hand, they are non-trivial.
Okay, well, I'm spending more time on this simple problem than I planned, but since a question appears, let me state a theorem of Kogan. Well, I'm actually providing an elementary reformulation. So if we have an n times n matrix of rank k, then in order to obtain an n times n matrix of rank n, we have to change at least m minus k numbers on the diagonal. Change at least n minus k numbers on the diagonal. So I hope this picture will be will be clearer and more interesting than the formal statement. Let me say it again. We have one matrix n times n of zeros and units. Another matrix n times n of zeros and units. They coincide outside the diagonal. So only diagonal elements can be changed. And this matrix has rank k, this matrix has rank m. Then at least this this amount of numbers on the diagonal are changed. We can change rank significantly by changing small amount of numbers on the diagonal. And in this form, this is a simple consequence of subadditivity of rank. Well, and now I think, well, using this theorem, it is easy to construct the algorithm. I don't want to give details because I would like to pass as soon as possible to more complicated, more interesting problems. Is it fine? Well, all papers are available on Archive, so if you are interested, you can find the details there. So another subject is also elementary. It's module to embeddings of graphs to surfaces. But of course, I'm aiming at embeddings of k-dimensional complexes into 2k-dimensional manifolds. So it's just an introduction. I will say it very briefly. So here are embeddings of graphs to surfaces. For example, K5 and K7 on the torus, or the right-hand picture, it's K6 on the Möbius band or on the projective plane. And let us now define a Z2 embedding. So first, what is, well, okay. Let me define a Z2 embedding. A general position graph drawing, that is a general position map of a graph to a surface, a map with self-intersections. Such a drawing or a map is called a Z2 embedding if the drawings of every two non-adjacent edges intersect at an even number of points. So these slides are written for non-specialists in topology, for specialists in graph drawings, in computer science, and they use this language of graph drawings, drawings of points, drawings of edges. But for mathematicians, these are images under some map, which is not assumed to be embedding. So of course, if there is an embedding, then there is a Z2 embedding, but not vice versa. So there is an interesting study of embeddings versus Z2 embeddings with interesting results. A striking result by Rado-Fulik, stating that there is a graph which is Z2 embeddable into this sphere with 4 handles, but not embeddable there. Well, although for the plane and for some simple manifolds, embeddability is equivalent to Z-mod 2 embeddability. And so a result is that, well, there is a result for complete graphs and for complete bipartite graphs. For complete graphs, there is a quadratic estimation. It's due to Fulik and Kinchel. And actually, this estimation follows from estimation for bipartite graphs due to Fulik and Kinchel. So n squared over 4. And although this is very similar to the Hewitt results on non-embeddability of graphs to surfaces, of non-embeddability of complete graphs and complete bipartite graphs into surfaces. But these results are stronger because they show non-existence not only of embedding, but also of Z2 embedding. And there is an interesting case when these results, it is known that graph K7 is not embeddable to the Klein model. And this particular result falls out of the general proof using Euler formula. It cannot be obtained using Euler formula, and I presume it is obtained using this very method involving intersection form of a manifold. Okay, I think I will omit idea of proof of this result. Well, I will only say that it uses the intersection form, and somehow, if there is an embedding of Kn into the surface, then we construct a matrix out of this embedding. A matrix uses intersection form and our drawing. And we do know some linear relations on this matrix. And therefore, pure linear algebra allows us to obtain such an estimation. We have a matrix with some relation, with some relations, and we obtain quadratic estimation on the rank of this matrix. And of course, this matrix is obtained by intersecting some cycles in the graph Kn, or rather of its images. So this is the gram matrix of some homology classes, and then the rank of this matrix is at most the rank of the homology group of the surface. That's the idea. And of course, this is very interesting in high dimensions. There are analogous high dimensional results. I will only briefly mention them. So here is the classical Hewitt inequality for embedding of complete graph into surface. And there is, a high dimensional analog of this result is called the Kuhnel problem, or even the Kuhnel conjecture. Kuhnel conjecture that if the complete k-dimensional complex on n vertices embeds into high dimensional sphere with G handles, then G is estimated by the constant depending on K multiplied by n to K plus 1. And here, the high dimensional analog of the sphere with G handles is the connected sum of G copies of the Cartesian product of two spheres. And until recently, only linear estimations were known in the situation. That is linear, even weaker than the Hewitt inequality. And with Gender, we obtained a quadratic estimation like that. So I think this is most interesting result of this talk, but since I already explained it with some yeah, since Svetoslav and I already explained it with ideas of proof at this geometry seminar, then I will only present a statement here. And now I come to the main point of my talk. Do I have some time left? 10 minutes, right? Very, very good. So, in fact, what I'm going to talk about is a general criterion for embeddability of K complexes into a 2K dimensional manifold. On one hand, of course, it's very good. On the other hand, it's perhaps right to point here that this general criterion does not make a result like this simple. So it reduces the problem of embeddability to some kind of Netflix problem, which is hard to obtain specific estimation. Okay. So the main part of this talk, embeddability of general K complexes to 2K dimensional manifolds. And here I present the results from Kogan and myself. And of course, there is a prehistory. There are many other results, including new results. Well, most notably by Patek and Tanzer, but also by some other people. And they are accurately listed in these very historical remarks in this paper. So for the rest of this talk, let K capital be a K-dimensional complex. Let n be the number of top dimensional faces, and M is a closed K-1 connected piecewise linear to K-dimensional manifold. So I will start with corollaries of the main result. So that main result, it is somewhat technical. So it does reduce the embeddability problem to some kind of Netflix problem, but before I state it, I would like to show that this reduction really works to produce some nice corollaries. So for K greater or equal to 3 and odd, a K-dimensional complex embeds into 2K dimensional manifold if and only if there are a skew-symmetric n times n matrix A with Z entries whose rank over Q does not exceed the rank of the middle homology group of this manifold. Recall that n is the number of top dimensional simplices of K. So this is now a matrix, and in which sense some elements of this matrix are known, or rather which relations on the elements of this matrix are required for a complex to be embeddable. And the relations are explained using a general position PL map of this complex to K-dimensional space. Well, and a technical thing, a collection of orientation on faces. And a relation is that for any non-adjacent K faces sigma and tau of K, the corresponding element of the matrix equals to the algebraic intersection of the images under the map F. So that's the result.
So the point of the first requirement is that the matrix which is given by the general position map has a sufficiently low rank.
Yeah, yeah. So we know some matrix elements, right? And we are free to take the remaining entries, those that is, we are free to change entries corresponding to adjacent K faces, in particular to diagonal elements. And by changing those elements, we are trying to minimize the rank of this matrix.
So when M is a two-dimensional manifold and K is a graph, something like this was known.
Of course, it was known. Well, first, this is not true, but the analog for Z2 embeddings and for Z embeddings, well, let's see. Well, it is known, but only recently by work of Akhmetiev and by work of fully contingent. So these are known results, but only recent results. Of course, I have to tell you that, well, I have to tell you that this result does not an algorithm, doesn't give an algorithm for recognizing embeddability, but not because of the obvious reason. One can think that there is an infinite amount of maps, and one has to check all such maps, and for the impossibility of such checking, one can check the embeddability. But that's not the case. Of this F, we only need the intersection cochain of F. That is the function F sigma intersect with F tau defined on the derived product of K. That is on the set of pairs of disjoint sigma and tau. And there is only a finite number of such cochains. Yeah, that's of course also incorrect, but at least for the two coefficients, there is a finite number of such cochains instead of infinite number of Fs. And so an analog of this result for the two embeddability does give an algorithm.
But are all of these matrices realizable by general position maps?
Of course. Well, any intersection cochain. Sorry. Of course, you are right. Not all of them. There is one company abstraction of K, and intersection cochain is realizable if and only if its difference with the one company abstraction with a representative of the one company abstraction is the sum of certain coboundaries.
There is an algorithm to tell whether it is the case.
Yes, and I think not only, yes, and even with Z coefficients, not only with Z2 coefficients, because there is an algorithm of, checking the solvability of a system of Diophantine equations over integers. Right, but here the collection, here this condition is quadratic. And for this reason, quadratic equation. Linear equations, that's difficult, but difficult but important. Of course, the intersection cochain, they do form an affine subspace in the space of all cochains. But this condition is quadratic. Sorry, I think I should explain this directly to Sergey after the talk. That's an important question, but I'm running out of time. And I would like to present simpler questions, some justification, some explanation of why this result holds, and at least indicate the general result involving Netflix problem. But actually, already this thing involves some kind of Netflix problem. So I will only state a classical result. I will only state a classical result explaining some ideas of that problem, or of that theorem. So that theorem is about embeddings, honest embeddings, not Z2 embeddings, not Z embeddings, but it is proved using Z embeddings. So let me explain what is a Z embedding, what is Z2 embedding, and why these algebraic embeddings are useful to study ordinary embeddings. So a Z2 embedding was already defined. So a general position map of a K complex to 2K manifold is called a Z2 embedding if the intersection of images of any non-adjacent K faces is even. And a Z embedding is a direct analog. Instead of intersection, we have algebraic intersection. And of course, the faces has to be oriented. So the classical results state that for k equals or equal to 3, a k complex is embeddable into a simply connected 2k manifold if and only if the complex is z embeddable to this manifold. I think neither of those people stated this result. They treated the case of Euclidean space, but the general case is proved analogously. And it's here why we have the codimension 3 requirement in that our main result. Well, the second is example of Melichov, for which k greater or equal than 2, there is a k complex, sorry, a k complex. Z2 embeddable, but not Z embeddable to 2k dimensional space. And that example is not hard, but an interesting example, hard example, is by Friedman, Krushkal, and Teichler. They show that this result is incorrect for k equals 2, and even for Euclidean space for n. That is, there is a 2 complex which is Z embeddable but not embeddable to R4. So that shows some insight into how that theorem 7.1 was proved. Thank you. Here I stop.
Какая размерность комплекса в теореме 7.2? Как комплекс? Это его размерность?
Да.
Два комплекса, это размерность два
И
комплекса.
тут опечатка, камерный комплекс был.
Ну хорошо, понятно.
Theorem 7.2 is something from long ago.
Yeah,
And
of course.
7.1 doesn't look like, it looks like it needs some more ideas.
Of course, yeah, of course. I only described the first, the simplest step. Again, I will be happy to explain the remaining ideas to Sergey or to somebody else, but not at the price of overextending this talk.
So, do you want to give a talk about this at the seminar?
Yes, I do, but this semester I have teaching on Wednesdays.
It can be a different day.
Okay, yep, very good.
What about Friday?
Well, it's reasonable for me. I have teaching in the independent university, but for once I can, well, invite my students to this seminar.
Thursday?
Yeah. Thursday is good. I'm free.
Ну, в принципе, мы
Well,
в пятницу собираемся.
I'm sorry. Maybe we could ask for questions. Well, some.
Ну, в среду. Там,
Shall I do this?
Накладка. Но вообще-то в среду 5 часов обычно получается.
Да, но вот Аркадий хочет четверг. Можно. Один дальше.
Ну, надо смотреть, по факту сейчас трудно сказать.
Maybe we ask questions of participants. Dear colleagues, thank you for your attention. Are there some questions? It seems to be known.
Okay.
Even Professor Wei Luo doesn't ask questions.
So if there are no questions, let's send the speaker.
Вот Володя Чернов